Always ready.
Okay. Okay. Hello, everyone. We are delighted to have Klim Efremenko from Israel presenting today. He is a professor of computer science at the Ben-Gurion University. His main research interests are in error correcting codes and information theory, and his current research focuses on error correction for interactive communication and locally decodable codes. One cool thing about him is he got a huge grant, so he's looking for postdocs, and all of you are welcome to apply. If you want to sleep on beds of cash, this is your guy. Okay, we can start.
Okay. Actually, situation in Israel is not that bad, but anyway. So today I'm actually going to talk about some work which is not my main research focus. I'm going to talk about hypothesis selection, and it's more related to machine learning, but I think it's the most basic question in science. So, first of all, this work is joined with Yatracos, Moran, Olivier Bousquet, and Mark Braverman. Okay. Sure. Okay. So, what is a common challenge, like what people have in science? So usually, what we have like some observations from some statistical model. So you can think about this as some distribution. We have some observations from some distribution, and we want to find a model which is best describes our distribution that we have. But the distribution that we have, we don't see it. We only see observations from this distribution. Okay, so this is, I think, the most like basic question that people deal with in science. So you can think about when you have several physical hypotheses that explain the nature, or something that explains some chemical reactions and so on. So this is like what we have. So now let's make an abstraction into the mathematical world. So what means what question we are going to deal with? So the question we are going to deal with is the following. We have several models. When I'm saying the models, you can think about several distributions, and we have observations from some distribution P. So candidate models Q1, Q2 up to Qn, you can think of them as you know them. So you know their distributions, you know exactly how they are distributed over the domain. And the question, can we automatically determine which model is better explains our model P? Which one of these Q1, Q2 up to Qn is a better model for P?
So Klim, when finite is crucial to your analysis, the candidate models being finite, is that crucial to your research now?
That what?
Keeping the probability candidate models to be finite, not an infinite collection.
So for this question, it's crucial that number of distributions is finite. So here we are going to deal only with the question how to pick one of a finite set.
Finite set, okay.
So okay, so like we would like to ask this from infinite set. The problem here is like giving precise mathematical definition that we can give some non-trivial answer like better than you cannot do anything is like hard. So if you have like general infinite set, it's just impossible. So you need some. So it's also like in terms of computer science, like how you need to get to the question how you describe this infinite set, but in general it will be just impossible. So but yes. So the answer to your question is yes. So hypothesis selection is abstraction of such question. So what we have distributions, known distributions Q1 over some domain X, and P is unknown distribution over domain X. And here it's better if you think of X as infinite size domain. And our goal is to determine which one of these QIs is the closest distribution to the distribution P in total variance distance. Okay, so what we can do, you can push a button to get a sample from P, so as many times as you want, and your goal is to find the closest distribution to P. And closure here in the total variation, and total variation is what one can think here as the definition, but total variation is you can think of it as the L1 distance between two norms. Okay, it's 1/2 of L1 distance. Another way to describe it is it's a maximal advantage that you can get between one distribution and another. So like it's a maximum over all subsets of X, such that the probability of A under P is bigger than probability of A under Q. Okay, so this is a total variation distance. So any questions about the question we are going to try to solve today?
Since you're in the information theoretic regime, so the only minimum number of samples, the algorithm can be brute force search also, or the algorithm also has to be efficient.
Okay, so the thing is, if you think of say this X as infinite domain, okay, so sometimes in order even to so what's the problem? So you cannot brute force. So even if you have like infinitely many, like if you have not infinitely, but any finitely many samples, it's not clear that you can solve this question. Yeah. And in fact, you cannot. I'm going to say this. So
sorry, go on.
So like what we said, let's zoom in and let's think what you have only two distributions.
Wait. Can you say something about other distance metrics like earth mover or some scale divergence or something like that?
Actually, no. Like I might going to talk about this, but what I want to say here is that if you can find so like somehow like total variation is probably the hardest out of all metrics. Okay, why it's the hardest? Because like if you know the total variation between two distributions is small, it means that any function of so if you have what it essentially means, it means that for any function f, if you want to ask what's the probability of f of x equals to f of y, where x is drawn from P and y drawn from Q, it's a maximum probability that these two quantities will be non-equal. So yeah. Somehow, like it's you can think of total variation. It's somehow the hardest metric you can have, the hardest advantage. But I'm not sure like what happens if you want to compute different matrices. I believe its question becomes easier, although like probably not much easier.
Okay.
Okay. So what would be like a natural approach when you hear this question? So we want to find minimum between distance between total variation distance from Q1 to P and the total variation distance from Q2 to P. So naive approach would be to estimate both distances and output minimizer. Does anyone see what would be the problem with this approach?
How would you estimate the distances?
Exactly, it's impossible. So the problem, like with with this approach is that if you want to estimate total variation distance between some distribution to P, we need approximately size of the domain samples. So it means that if you want to estimate total variation distance from some distribution to P, when our domain is infinite, it's impossible. So let's even think about the following question. One question is one thing is that our distribution P is uniform, total uniform over 0, 1, and another is that it's uniform over finite subset of 0, 1. Okay. So remember that you don't know distribution P, so you know nothing. You only can get samples from distribution P. In case that it's uniform over finite subset of 0, 1, you need at least a square root size of x in order to get Bernoulli paradox, in order to see that it's uniform over finite subset of 0, 1. So if our finite subset is large enough, then you'll just uniform distribution over 0, 1 and uniform distribution over a finite subset of 0, 1, you'll look for you exactly the same.
Okay.
Okay. So now the question is like, is comparing total variation distance is possible at all? Like when you look on this question, like it looks like, wow, it's essentially like impossible. How you can find, how you can see what is better. So our main result that we are going to see today, I hope we will get to see all the details, or at least most of them, is that we have many distributions, and P is a known distribution in sample axis. And let's define opt to be the optimal solution, the best out of all these, the best distribution out of these QIs that is closest to P. Okay, so now what we are going to do, we are going to give improper algorithm. What means improper? It means that we are not necessarily going to give you one of the QIs. We are going to give you some distribution such that this distribution is close to P. How close? It close by distance at most twice times optimal distribution. There is some factors epsilon, so it's twice times optimal distribution plus some factor epsilon. And the main thing that we are going to have here is that we are going to have here a number of samples that we'll need in order to make such an estimation. We'll need only log n divided by epsilon squared. And what I want to say that this sample complexity is essentially optimal. So it's up to like constants hidden inside this O. It's an optimal sample complexity that one can hope for to solve this question.
What is the representation for Q?
Representation for Q. Okay, so it's a not okay. Here it's we assume that it's a given you in some way. So it's a not computational question. It's a question that asks about sample complexity. Okay, so we didn't. So you can think about this in a different ways, but what we'll need to know is like we need to be able to approximate what's the probability Q on some set A.
Okay.
So and you can assume that you have access what's the probabilities of Q on sets A, and you can have access to some linear combinations of Q, but or you can think of Q as some distribution that is given as some function. But it's what I want to mention here. It's not a question about computational complexity. It's a question about sample complexity. So how many samples do you actually need in order to find such Q?
Now, if you knew that P belonged to some parametric family, would the problem become easier?
Yes, of course.
And you have
If
results.
you do, what?
Are the results well known in that setting?
So okay, so okay, it depends. If you know, for example, that P in some parametric family with a finite VC dimension, then you can you can just learn P up to constant epsilon, and you don't need the class of distributions. Okay. If P is in some family with so okay, so it's there is like the whole theory of machine learning. So and like probably the most like it's a VC dimension that measures if you can learn this family or not. Okay, so and it's probably the most classical results that you'll see in machine learning. And in case that P is not in a family that with a finite VC dimension, that I don't know like how this question like will tie it with our question. So like it's actually a good question. Like, can you describe sets of families such that for these sets you can make a fast that you can make a very fast approximation or even finding optimal distribution that is closest to P? I think it's a good question. But yeah, any more questions about so what I want to say here, it's like I'm of course I'm omitting a little bit details because like okay, of course our algorithm can there is like some factor delta which I'm omitting that our algorithm can. So when you are dealing with probabilities, it always can happen that although like you have uniform distribution, but you press like 100 times and each time you get number less than 1/2. Right, so but it's a very small probability. So there is some factor delta that so that our algorithm will fail and mixed it here. But I'm just this is not an important parameter, so I'm like omitting them for now. Okay. Okay. So first, what is known, and like previous classical work by Yatracos asked this question and asked this question to have a proper algorithm. When I'm saying proper algorithm, I mean that algorithm at the end of its running has to output one of the distributions out of Q1 to Qn, and Yatracos algorithm shows that there exists a proper algorithm which outputs Qi such that the total variation distance between Qi and P is at most 3 times optimal. And this algorithm has optimal number of samples. And actually, like this algorithm is surprisingly simple. You'll see our algorithm; it's way more complicated than Yatracos algorithm. Okay. And before us, so the question was like, does this factor 3 is necessary? And Bousquet, Kane, and Moran showed that there exists improper algorithm Q. So if you don't insist to output Q1 of the list, but you can output any Q. When there exists a proper algorithm Q such that it outputs there is a proper algorithm such that it outputs Q, such that the total variation from Q to optimal is at most twice factor. So you get factor to approximation. The only problem with this their algorithm that the number of samples they needed is exponential. So you can think of n or number of hypotheses to be like very large. And the number of samples they needed was like about square root n. So it was way far from optimal. So if you see like optimal is log n divided by epsilon squared.
Do you know if there is a proper algorithm that beats 3?
I know, no, there is not. It's an excellent question. Here I have like, there is like always like all questions are good. Some questions are great and some questions are excellent. Excellent questions, it's the questions that you have slide for. So like great questions, it's the questions that you have answer for, and good questions that you don't have answer for. So it's an excellent question. I have a slide for it. So yes, so factor 3 is necessary for proper algorithms. So you can show that if you can show that if you insist that your algorithm will output one of the QIs, then you cannot achieve a better approximation than factor 3. And factor 2 is necessary for improper algorithm as well. So what we are getting is tight. So like so we cannot like you cannot do some other algorithm will get better factor. So we essentially get optimal sample complexity and the optimal approximation factor. Okay, so far I described you the results. So I would like you to like to see that you actually understand like the main result before we are going to like go to dig down into the proof of this theorem. Okay, great. Okay, so
one question for you. Suppose the problem was, okay, I have these distributions Q1 through Qn, and I have this distribution P, and I want to find the distribution which has the closest mean to the mean of P.
That you want to find distribution that is what?
The closest in mean.
Expectation.
In expectation. Is that a much easier problem to all the QIs that are given?
What do you mean by closest in expectation? In expectation over X, I think it will be the same question. Maybe not. No, I think it's, wait. No, I think it's, it will be. So you just want, wait. So you just want Q that is closest in so such that expectation between P and Q is the smallest?
Yeah. So I guess, yeah, all the Q.
Then it would be easier, right? Because you can just approximate what is the expectation between P and P minus QI, right? So you can just, you can approximate expectations.
Right, I mean, you're giving me then n expectation numbers, and I'm trying to see which one is the expectation of this samples, which one is it closest to. Yeah, that should be easy.
So like, okay, the thing is the following, like, the question is like, what, if you have like, say, you know, so in case of expectations, right, it's a question about can you approximate expectation? And in this case, it will be a question about a distribution P. So if distribution P, if distribution P will have like rare events with a high values, then you have nothing to do, right? Because like, for example, so like I think expectations, it will be also hard. It's maybe even harder. I think like, okay, so
Boundary is
something would be.
no, the problem like what happens if you have like a very small on these QIs, you have a very small spikes.
Yeah, right.
With very high values, right? So in this case, you will not be able to approximate this at all. I think in case of
Maybe a bound on a moment or something. A known explicit bound on a moment will work.
When you can probably do it. So it's it's a little bit different question. I think I don't believe it. Like I don't believe it would be hard, right? I don't believe like once you'll phrase this question correctly, I don't believe this question will be hard. So it will be either impossible or it's possible, but I believe it will be just I just believe it will be easy, because like you'll ask like your approximate expectation, what's the probability that your approximation is correct? That's all. Okay, so let's go now. Unless someone else has a question about our results, let's going, because I want to show you like it's a the proof is very nice because it's like requires some very interesting, it has some very interesting relations to information theory and it's relations between information theory and between topology. So it's interesting. So let's see. I want to, let's assume that I have some family of sets of X. I want to define an F distance. I want to generalize the total variation distance and want to define F distance. If you remember, total variation distance is a supremum between P of A and Q of A, where supremum goes over all possible sets A. Here I'm going to define D of F, where supremum goes over all sets A from some family, from some family. So you have, let's assume we have a family of subsets of X. In our top where will be finite. And we are going to define D of F between P and Q supremum over A in F. Some properties of this distance. One, here should be F. Anyway, one, it's triangle. It admits triangle inequality, so it's actually distance. Second, this distance is always smaller or equal than total variation distance. And again, because definition of total variation distance is when F is all subsets of X. Okay, and the third property that is will be crucial for us is that we can actually, unlike total variation distance, we can actually measure this this distance. What it means? It means that we can actually, if you have sample access to some distribution P and some distribution Q, we can just estimate what is the probability of A under P and what's probability of A under Q from these samples, and we can, like, it's enough if you want to get 1 plus minus epsilon approximation for probability of A, you need 1 over epsilon squared samples. If you want to have this approximation for family of size F, you need log F divided by epsilon samples. It's a very simple Chernoff bound. And more generally, if you have some bound on VC dimension of F, then you need VC dimension of F divided by epsilon squared samples. Okay, so this is what we are going to work with. Now, what we are going to do, we are going to define the following distance vector. For any distribution Q, we are going to define vector V of Q. It's a following vector is a total. So we are going to calculate this distance of this Q to each of Qi's. Okay, and the following way we are going to define V with a subscript F, where we're using instead of when V subscript F is instead of total variation, we are using this distance df. Okay. So we have, say, you can think here, it's that we have some distributions Q1, Q2, Q3, Q5, and you have some distance, what's the total variation of our distribution Q for to each one of each one of them. Now I want you to see the following property. That because of the distance d of f, v of f of q always less than v of q.
We have a minimum missing in the definition of v of q.
What?
It's a vector. It's a vector.
It's a vector. I'm actually now I'm going actually to look on all. No, this is important. I'm actually now going to look on the whole vector. And the thing is, like, I will be able to calculate VF of P, where we have P is as our distribution. Okay. So here is what we have. We have Q is a class of known distribution. And now what I want to convince you is in the following key observation. Let's assume that we have some distribution Q that satisfies the following property, that V of Q is at most V of P plus epsilon. When I'm claiming that total variation distance between Q and P is at most twice the optimal distribution.
What does the hypothesis mean? V was a vector.
Coordinate. So when I mean that one vector is less than another vector, I mean coordinate-wise. Plus epsilon, it means in each coordinate it's less than V of P plus epsilon. Here I mean coordinate-wise. So I'll prove it. It's a very simple proof. It's very simple triangular inequality. Corollary of this key observation that it's sufficient for us to find Q such that V of Q is at most V of P plus epsilon. So, and this is what we are going to do, like, for the rest of the talk. Now let's see the proof. Okay, so we have let's UI. Okay, this is this. Do you see my mouse? You don't, right?
We see your mouse. It is.
So you have QI, and this QI is an actually optimal distribution. What it means optimal distribution? It means that total variation between P and QI is less than total variation between P and QJ for any other J. Okay, so it's optimal. It means that it's equal to V of P at coordinate I. Now, V of Q at coordinate I by what we are given is at most v of p at coordinate I plus epsilon. All right. So this distance between q and qi, it's v of qi, right? It's the total variation between qi and so it's a distance. It's a total variation between q and qi. We know that it's less or equal than v of pi plus epsilon. So we know that this h, distance of this h is at most v of pi plus epsilon. Distance of this h is at most v of pi. So this can be at most twice v of p at point I, and it's at most twice of optimum. Questions? Okay, fine. So we have a triangle inequality. So now how we are going to do this? We are going to do this in a sequence of so how we are going to find so now as you remember our goal is to find the q such that v of q at most v of p plus epsilon. And now what we are going to do, what we can do, let's now consider the following convex sets. First, convex set, q of total variation, it's the set of all possible vectors that we can for any distribution. And the second convex set that we will see, it's under VF of Q. So we can define these two convex sets. Q of total variation, right? It's all possible vectors for any distributions of distances to all other distributions that we have. And the same we can define for any subset F. And we have some nice properties. First, the way how we defined it's convex and upward closed, and also QF is convex. And up, so we defined it. So okay, upward closed. We defined it to be upward closed, and we also know that Q of F is contains Q of total variation. Now, what we want to do? We want to find here some distribution Q. So we want to find here in our Q total in this gray area. We want to find some distribution Q such that it's at a distance at most in L infinity distance at most epsilon from Q of from V of P. Okay. And once we'll find such distribution, we'll be done. How we are going to do this? So the problem. What was our problem? We have no idea how to find the V of P. But what we can do, we can actually for any let's say for finite and not large enough set F, we can actually calculate VF of P. Right? Because we can just make an approximations of some sets under sample access of P, and we can calculate this vector VF of P. And we know that VF of P is always less or equal than the V of P. Right? So what is our goal? What you can see is we want to find this point VF of P such that it will be epsilon close to our gray area, to the area of all possible. So we want to find we'll try to find some set F. F is a set of subsets such that VF of P will be epsilon close to the gray area of V of Q of total variation. By the way, note that we know this. This is just so. Here we know everything. Like we know this gray area Q of total variation, and we know this area of Q of F. So it's something that we can think of it as we know it, because there is nothing that is unknown. So we are given all our distributions Qi, and therefore we can just construct these areas. Okay. So, and we'll try to play a game here, pushing this. So we are going to add more and more sets to the subset F, such that it will push VF of P closer and closer to our region. And let's see how we're going to do this. So what we are going to do, we are going to find each time we are going to find larger and larger. We are going to find the sequence of subsets, F0, F1, so on up to Fi.
So you're actually finding Q such that VQ is at most VFP plus epsilon?
I'm actually yes. I'm finding such that V of Q at most VF P plus epsilon. Yes, this is what I'm finding.
Okay.
Under some set F, yes.
Okay.
Okay. What we are going to do, we are going to produce a set of points Ui, such that Ui is VFI of P, and it's at most V of P plus epsilon. And each time Ui is going to be bigger than Ui plus minus 1. Okay, so why it's bigger, it's very easy because of inclusion of these sets. It's very easy to see because essentially by definition, that if you increase the set Fi, you can only increase vectors Vfi of P, because you are just taking maximum over a bigger amount of sets. And another thing that we'll see that we can have is that Ui minus 1 is at least epsilon in L infinity norm. So how it's going to work? We start with U0 to be zero vector. So and then we are increasing until we get close enough to this area. Then we find some distribution here, and we'll be done. The problem, this requires n divided by epsilon steps. Why it requires so many steps? Because if you are increasing only in L infinity by epsilon, means we are only increasing at least one coordinate by epsilon. And if you have n coordinates, then it may take us n divided by epsilon steps. Okay, so now this is like the general idea how we're going to do this. And now how we are doing this. We are going to do this with following separation theorem. And this theorem is as follows. Assume that you have some set C, which is convex and disjoint from Q total variation. Then we can find the set F of size at most n, such that this set separates C and Q total variation. What does it mean? It means the following: you have this Q of F, okay, and this Q of F is disjoint from C, and it contains Q total variation. So it separates this C and this. So we can always find this. Why it helps? And again, note that VF of P can be estimated given log n samples from P, log n divided by epsilon squared if you want to get approximation of epsilon. So now, do you see now how using this separation theorem we can produce our set of points UI? Does anyone see this?
How does this ensure that you in L infinity?
Once again?
Do you say why this means that you increase in L infinity?
Why what?
Why would
No, that's the set, right? The set has the epsilon. C is the epsilon cube, so you have to fall outside that.
Oh, okay, yeah, I see.
Making epsilon progress. The orange set is the thing that you don't want to follow.
Okay, yeah.
Because like at the end of the day, what I want to be in at a distance epsilon in L infinity from our set Q total variation. This is why I'm increasing only by epsilon in L infinity.
Yeah.
Okay, so how now our algorithm will work? So we actually don't need this maximum. So how our algorithm will work? Each time we have UI, okay, and either this UI, either ball L infinity ball around UI intersects Q total variation. In this case, I claim we are done, or it's not. If it's not intersects, we can apply separation theorem and get another QF, and then we can approximate VF of P, get a new point, VF of P. Now, in this VF of P, either we are done, or either it's L infinity ball is intersects our Q total variation. If it's not, we can apply again this separation theorem, and so on. Okay, so is it clear? Okay, let me maybe give some very simple example. Let's assume that we have our domain X is a domain over 3 elements, 1 to 3. Q1 is a distribution which gives all its weight on the first element. Q2 is a distribution that gives all its weight on the second element. I'm claiming that for all Qs, it holds that total variation between Q and Q1 plus total variation Q and Q2 is at least 1. What is how we can witness this fact? We can witness this fact by looking on the subsets which is contain only set 1 and subset which contains only set only element 2. Right? In this case, let's assume that say P of 1 is 0.4, P of 2 is 0.5. Then what we'll get total variation between P and Q1 is 0.6, total variation P and Q2 is 0.5. So we'll get our next point UI, right? If you are using these witnesses for fact that total variation is at least 1, but our UI is essentially like under this line. Then now when we are approximating our total variation with these two sets, we are going to get next UI, which is above this line. Okay. So what we'll have here, we'll have here some point UI. If we are not done, we have some line that separates our UI from our. So now we are completely in the realm of geometric problems. We have some point UI, and if in a ball of L infinity ball of this UI is not intersect our convex set, and here I'm not going to use any properties of Q total variation besides that it's convex set. If we are not intersecting, there is a line that separates this. And now what we can do, we can use separation theorem to find a next point, which is on another side of this line. Okay, and this is how we are going to continue until we'll have like no separations. It means that we are done. Okay, so here is our cutting game. So now, okay, now you can, anyone who is like already sleeping, you can, wait, how much time I have? I have 10 minutes.
Yeah.
Okay, okay, so now, okay, I will try to do it a little bit quick. Now, like what we have, essentially, we have a following interesting game. We have what's called the cutting game, player versus adversary. And it plays in a round. At every round, player picks a half space HI that separates our ball pi and ball around of radius epsilon pi from our set S. Adversary picks a point on another side of this line. When we pick another line that separates this point and so on, player wins when intersection of ball of pi and around epsilon is intersecting our set. And the question, how many rounds do we need to in order to win this game? So in order to solve this game, we can look on following dual game. And dual game is the following. So we can see it as, instead of looking on points and trying to be closer and closer to our set, we can see it as a following question. For every point, there is a set of lines that separates this point from our convex set. Once there is no line that separates our point from convex set, we are done. So now, instead of this, we can see it as a following dual game. So at every point of time, we pick some point xi, and adversary essentially cuts. So you can see it as you have some body. We pick some point xi inside this body. Adversary cuts out this point with some epsilon neighborhood. And we continue this game until our body is empty. So here I have actually examples. So first round, let's say we picked this point, and adversary cut it this way. Now we pick this point, adversary say cut it this way. Pick this point, adversary cut it this way. Pick this point, he cuts it this way, and we are win. So we are win in total of 6 rounds. Okay, and what we want to do here, we want to reach, we want to win as fast as possible. Because like number of samples here. So let's put it together. So if we can win, if it takes for player to win in R of like in R rounds. Oh, and here like L infinity norm will be translated here in a dual game to L1 norm. When there exists an improper algorithm Q such that outputs Q such that the total variation of this Q from P is at most twice optimal, where number of samples that we need is log n divided by epsilon squared. This is the amount of samples we need for each round, times number of rounds we need in order to win this game. Okay. Now I will just say how we can do this, how we can win this game in L1 norm. And what we'll do, okay, I don't think I have lots of time. I'll just tell you what we need. So essentially, every time, what we are going to do, we are going to pick a point with maximal Shannon entropy. And it turns out that like it's actually not very hard to see it, but like somehow it took us lots of time to get to this. If every time we pick a point with maximal Shannon entropy, our starting point has Shannon entropy is of log n. Our starting point is 1 over 1 over n, so on. And each time we can see that we are going to increase, to reduce our entropy by at least epsilon squared. And this follows from a very simple application of Pinsker inequality. And therefore, after at most log n divided by epsilon squared rounds, we are going to win. So here it's actually proof, but I don't believe I can it will take me more than 5 minutes. So but essentially after at most log n divided by epsilon squared rounds, we are going to win this game. So altogether, what it will give us, it will give us algorithm that runs in log n squared times divided by epsilon to the 4th. Okay. In order to get actually optimal log n divided by epsilon squared, we need to be like so it's here we need to do a lot of heavy lifting, but essentially we need to be very careful. So we need to see that at some rounds where we are not progressing very much, we don't actually need to use that many sets to approximate, and we don't need that good approximation. And in rounds where we are advancing a lot, we need a good approximation. Okay, so questions about algorithm. Okay, I want to give here some questions that I believe that were interesting, and like you may ask like another questions. So one thing is that what happens on so we talked about cutting with margins for L1 norm. So what happens if we want to play? So I believe that this game of cutting with margin, it's an interesting geometric game. Okay, anyway, so cutting with margins, it's an interesting geometric game. And I wonder what happens if we want to ask these questions for another norm, like LB norm or L0 norm or any other norms. And I believe that using like some extension of KL divergence, which called Bergen divergence, will help here, but we didn't do this. Another question is the following. Even if the original like a naive algorithm where you each time increase by epsilon, right? So you start with n sets, and you get approximation of epsilon with n sets. Then you get another n sets, and you get approximation epsilon with n sets, and so on. So in total, you're going to get about n squared sets. So getting approximation of n squared sets, if you were giving them in advance, it takes our only twice log n divided by epsilon squared samples, right? But the problem here is that what people are not allowed to do in science is that we are doing it adaptively. So it means that so we're picking first sets, and what our next set is depends on the samples that we get. So we cannot reuse samples that we get for first sets for the second chunk of our sets. And there was a very influential paper about adaptive data analysis that shows that if you're not actually needs your approximations to be tight, and it's enough for you to approximate the size of sets up to plus minus epsilon factor, you can reuse some of your samples. So it was not enough for our case, but I believe this case is an interesting case where we can ask whatever it's possible to do some better adaptive data analysis than general results that are known. I think it's all. I don't want to run over time. I think I'm good on time. Okay, thank you. Don't hear you. Any questions? I hope it was not too fast.
For finite sets, so are all the steps now even efficient also? Or when x is finite, if I'm allowed to use polynomial in the size of x time, then it seems every step.
When x is finite, things becomes easier. And when x is finite, you can always solve all these problems in polynomial time in size of x.
In the size of x.
Yes. No, I don't think you can solve it in. You need this. If x is finite, you need in order to see that it's finite, you need at least a size of number of samples square root of size of x, because before you get square root of size of x, you don't see collisions, so you cannot use the fact that it's finite somehow, it's on intuitive level of things.
No, I was just wondering that this algorithm, when is it also complexity, in terms of complexity to complexity also efficient? So finite x certainly is this algorithm also is efficient. Or it's running in poly x.
Once again? Once again?
So if
don't hear you well.
The Q's are given as tables, like probability tables, then when x is finite, this is running in time poly x. This is your algorithm.
You're asking about running time. I don't think we thought about running time at all, because for example, we thought a little bit about running time, but for example, computing this region, it's not clear how you do this. It's not clear how you find. So we didn't ask ourselves about running time. Okay, we tried to ask this question. We just didn't found how to formulate this question that it will make sense. This is what I want. So if you have if you can ask a question about running time that will make sense, I'll be happy to hear it, but I don't think we had a way. Wait.
So naturally, Q given as tables, So you're around, basically that thing that you're around time polynomial in the size of X.
So if X is finite, I think everything is simple.
Actually, not finite here, then it's
Taking time poly to just estimate P if you keep sampling, unless the probabilities are very tiny.
so yeah, then you can even just do, yeah, if you're about poly X, then. No, but there's the number of samples you still want to be. So there are two things, right? Number of samples and time. Number of samples you still want to not depend upon X at all.
I see.
So you would want the number of samples to be independent of X, only dependent upon the number of distribution.
Okay.
So the setup is that the number X is much larger than the number of distribution. That's
Yeah, maybe you can ask this question when you have a number of samples. When X is finite, and then we can ask what's the computational complexity. So anyway, we didn't deal with question of computational complexity. We only asked this question in terms of sample complexity. So how many samples do you need in order to approximate this? We didn't ask ourselves about computational complexity.
But I had trouble following the last part about adaptive analysis. What are you trying to do? Are you trying to remove the log-in factor? What is the challenge there?
The last part, it means, wait, where is it?
Discussion slide.
From
Slide 45. 45.
Here, so you want to remove log n factor and epsilon squared factor.
Next one.
What?
Next slide.
In next slide.
Yeah.
Here with adaptive data analysis, I want to develop a theory. Okay, so there is a very nice theory that it's in fact very interesting that samples sometimes may be expensive. So, and it says that sometimes, like when you are doing experiment, you can, although in general, it's not so. It's a basics of a science, right? So you're not allowed to use the same sample. So you can sample some samples, see them, then make hypotheses, but then you cannot reuse these samples to test if your hypothesis is true or false.
Yeah.
Okay. And there is a very nice area called adaptive data analysis that says that if you're not using all the data from these samples, but you somehow obscure these samples, okay, namely you're adding some noise to these samples, then you actually can reuse these samples. Then you can reuse these samples for next for more steps. Okay. And here I just want to design a general theory that. So I would like to, it's not a question about improving this concrete algorithm. I just believe that this concrete algorithm is a good example for algorithm for which you can ask whatever you can design some general theory and which will be maybe generalized for many other algorithms. So it's more about designing the theory.
Okay. More questions?
Sorry, so what are these generic adaptive data analysis techniques trying to do? What kind of problems are they solving?
Okay, I think it works for, so here is what they say. They say the following: if your queries are differentially private, it means essentially that each query you get, you add some epsilon, some epsilon noise. Then when you can do some when you can reuse these samples something like square root n times something like this. I don't remember exact number, but you can reuse these samples some amount of time. So I'm sorry, I will not be able to like on the fly to say correctly. No, I will not be, but essentially it says that if your samples is obscured, it means that you don't get exact samples from X, but instead you're getting a sample from X with epsilon noise. Then you can reuse these samples like square root n times. This is what this theorem says, and it's a very general theorem. So like theorem says that no matter what your tests are, so you can still reuse these samples as long as they are what you get is obscured.
More questions? So let's thank this speaker then.
Thank you very much for coming.
Thank you, Klim. It was a great talk.
Thank you.
Bye.